Hello, it's Professor Todd Elliott once again, and in this video we will look at the property of reactance. So we'll be talking about inductors and capacitors and how AC frequency affects them. This presentation, the slides I'm using, I don't even remember when I made them. Could be 20 years ago, 15 years ago for sure. I'm just finally getting around to making a little video on them. So, but everything in good time, as they say. Okay, a little bit of a review. Resistance. The unit of resistance is the ohm. It applies to anything resistive, so literally a resistor, conductor, transformer winding, it's all resistive. The phase or phase displacement angle is 0. When we're dealing with AC circuits, knowing the properties of the component is absolutely essential. Capacitive reactance, so we're talking about a capacitor. Again, the reactance, the unit is, ohms, k ohms, milliohms, things like that. The reactance angle is minus 90 degrees. And it's important that you note the minus angle. Capacitive reactance XC, 1 divided by 2 pi Fc, where Xc is the capacitive reactance in ohms, 2 pi is a constant, F is frequency in hertz, C is the capacitance in farads. So this means then that the reactance of the capacitor varies with the frequency. Unlike a resistor, we're not talking about very high frequency effects. The resistance is the same regardless of the frequency. Capacitor, the reactance decreases the higher the frequency is. Okay. Using that formula, for 100 microfarad, micro is 10 to the minus 6 capacitor, take the frequency from 60 hertz to 10 megahertz and then plot those results. What do you see? When the frequency is 0, the reactance is infinite. That's like DC. That's why capacitors on DC, they charge and then they block the DC. This is why. And then as you increase the frequency, the reactance then decreases. Inductive reactance, motor windings, transformers, solenoids, coils, transformers. The unit of reactance is ohms. Applies to AC motors, transformers, inductors. Notice the angle is 90 degrees, but it's positive. Capacitor is negative, inductor is positive. You don't want to get that mixed up. Inductive reactance XL is 2 pi times the frequency F times the inductance henries. So 500 millihenry inductor, milli is 10 to the minus 3. Take the frequency from 10 hertz to 1 megahertz, work out the reactance, do the plot, and look there. You have a linear line between the frequency and the inductive reactance. So in the inductor, increasing the frequency linearly causes the reactance to increase. Impedance is when you have a circuit or a device that has resistance and either capacitive reactance, inductive reactance, or quite often both. Again, the unit of impedance is ohms. The component, it doesn't apply to a particular component, as kind of like the system, if you will. So if you look at a motor or a transformer, it has resistive resistive components, primarily due to the transformer windings, but it has plenty of inductive reactance due to the core and the magnetic field. The phase angle depends on the relationship between the XC, XL, and the resistance, okay? So easily determinable, okay? And the formula there is the impedance Z is equal to R squared plus X squared, where X is the total reactance, all square root, okay? Impedance triangles. And so here we have an inductor on the left, and we have the capacitor on the right. Okay, so notice that the resistor, look at the inductor, the resistor is the, goes on the x-axis, the inductive reactance XL goes vertically, so that would be, so this would be the resistance here. This is the x-axis. This is the inductive reactance here, and this here, Z, this is the impedance. So the impedance triangle gives us the triangle mathematical, it's a right angle triangle relationship between the real, the resistive bits, and the imaginary, the reactive bits. This here, this is called the impedance angle theta, easily determined by trigonometry. For the capacitor, notice the orientation is flipped, but the resistor is still on the horizontal x-axis, but I've drawn the x of c down because I said it had a minus 90 degree angle, that's 90 degrees, and this is the impedance. Again, that's the impedance angle determined by trigonometry. Now the books over the last 20 years or so, they sometimes they flip the polarity around when we get down to the power on the power in the capacitor and the power in the inductor. They agree on the impedance though. So if you picked up a recently published book, and I mean the last 20 years, they will show you the XL with the positive impedance angle and the XC with a minus impedance angle like I have shown you. But when it comes to the power, some of them will make the power in the capacitor to be negative and the power in the inductor to be positive. This is wrong. This is not the way I learned it. And everybody I know learned it the way that I learned it. Does it matter? No. And it's just a matter of, for whatever reason, the perspective was changed in how you're looking at it. And think of it like, does it matter if you visualize current flow as going conventional or electron? It really goes electron. If you have 1 amp going conventional flow left to right, and you have 1 amp going assumed going electron flow right to left, does it matter? No. So the important thing is when you're working with the reactive power in VARs, if you make the inductive power, the QL, to be negative and make the QC and the capacitor power positive, just do it consistently. If you wish to interchange that, then just be consistent. So I don't know why the change was made. I know I looked it up many years ago. It was an IEEE. There was a standard, and the standard used to say how I learned it. So anyway, I haven't gotten to power yet. My mind just kind of wandered ahead a little bit, but this is just with the reactance and impedance. So, okay. Simple formula, RC We have a capacitor and resistor in series, 5 ohm resistor, 200 microfarad capacitor, line frequency of 60 hertz. Calculate the X of C using the formula I showed you a bit ago. 1 divided by 2 pi FC. Calculate XL, or not, no XL, just RC. Calculate the impedance. So basically what that means is that this is 5 ohms. This is 13.26, and this is 14.2. So the impedance is a trigonometric relationship between the R and the XC, and if you just use the inverse cosine between the 5 ohms there and then the impedance there, that impedance angle is minus 64.3. Okay, skip ahead, do an RL. Okay, I'm just picking and choosing my slides. I'm not gonna use them all. So we'll end on this one. So series resistor inductor, line frequency 60 hertz, 400 millihenry inductor, 65 ohms. Okay. Draw the impedance triangle. So this is going to be 65. This is your calculated value XL, 2 pi FL, 150.7964. And then find the hypotenuse, right? And it's 164 ohms. And in this case, the impedance angle is a positive 66.7 degrees. Okay, we'll catch you soon. Thanks for hanging with me there. Okay, bye-bye.